talk about free fall motion. So physics people, you're going to see a lot of overlap, especially today, with just dropping an object, right, with force of gravity and all that stuff. Not a lot of new material. We just have to think about it as.
Are we doing it feet per second?
You will see both. You will see feet per second and you will see meters per second. Ugh, terrible. Okay, so let's recap first of all. If I asked you to find maximum distance, that was our warm-up problem. What did we do? Take the derivative, figure out if it's a max, and then plug it back into the original equation, okay? That's what you already did. What if I asked you to find the maximum speed? Okay, so first we think about velocity, right, and that derivative. But then what's going to be different about checking our critical points? Kind of. If I'm asking for maximum speed, okay, we're going to have to plug it in to the velocity equation with the absolute value of it. Okay. This is my reminder, if we are on an interval looking for some sort of maximum, the endpoints do matter, right? So we're going to do a maximum speed example, and then we will get into our free fall motion. This attached with free fall. Like free fall is essentially what we're doing today, but I wanted to add in these maximum ideas. Okay. Okay, so I want the maximum speed of this equation. Oh, look at that. It's the same one. But this time I want it on an interval just from 1/2 to 2. Sundays. Okay, so if we are looking at maximum speed, we want to find the critical points of the velocities. Okay, when we're talking about speed, speed is related to velocity, correct? So if I want the maximum of the velocity,
critical point of the velocity. No, we gotta take the derivative first.
So this is our derivative, right? We take the derivative of the velocity. Okay. Do we have any critical points? Okay, so no critical points because -32 cannot equal 0. If you actually had a t value, you'd set that equal to 0, solve for t, and you would have that to test. Okay? So, we have our endpoints to test. And we're not plugging them into velocity, we need the speed. So we plug it into the velocity and take the absolute value. So pods 1 and 2, please find me the speed at 1/2. Pods 4 and 5, please find me the speed at 2.
What about the lead? They gave you nothing.
Yeah, lamos.
Oh.
There's nobody sitting in pod 3.
I was like, where's pod 3?
I should hear calculators like. You wouldn't need to, I suppose. I guess I just expected it. Okay, Brady, you seem like you have your answer. What's the speed at 1/2?
Oh, I was doing the 2-1. Sorry. Yeah, it was fine. It should be easy.
Emma, can you help him out?
32.
Oh, both of you together. Carter, what about the speed at 2?
Go like that.
Or 16.
You got what?
16?
16?
No, I got a negative.
Oh, yeah, but the absolute
Has to
value.
be the absolute value, Brady. My bad.
So, we have a max speed of 32 at 1/2. Yes.
I keep getting 12 for one time.
Of 1/2?
Yeah.
So we have negative 32 times 1/2, which is negative.
Oh, you're getting that one.
Yep. Yep. Were you going back to the position?
Yep.
That would be the problem. Okay. So now we're going to talk about free fall motion, which is what is. I could like hear the something without me. What does free fall motion mean? What am I?
You're falling.
We're dropping an object. So we still have linear motion, but instead of left and right, we basically just have straight down. Okay? So we're going to basically throw something at the ground. Either drop it with no initial velocity or throw it with some sort of initial velocity. Okay? We're going to assume that the only force acting on this object is gravity. We are not going to deal with the size of the object or any sort of like air resistance or.
What about wind?
We're going to ignore it.
For the previous slide, if you had like critical points for the acceleration one, would you find the maximum speed at those values too?
Yes. If there was no interval, that would be the only place that you would look. If there's an interval, you use critical points and endpoints. Okay. So here we go. Could anybody tell me what the model is for the position of a free falling object?
A bit like an interval.
Okay, we'll get to the 9.8 soon.
That's a parabola.
It is a parabola. It's
Oh, I was gonna say.
Brady had it right on the tip of his tongue. Okay. Initial height, initial velocity, force of gravity. I'm probably going to write it backwards, but for right now I wrote it like this so we can think about, first we think about position, then we think about velocity, then we think about gravity. Right? I'll probably start with the negative 1/2 g squared. Okay. Okay. For this class, you will have two different gravities you'll have to consider. For meters per second, if that's your velocity, then we have 9.8 meters per second squared as our velocity. If we're working with feet per second as our velocity, then 32 feet per second squared is our acceleration. Okay, and since things are being pulled toward the ground, these are going to be well, the negative is going to be taken care of here. Okay, I've already taken care of the negative in the equation. So we have that negative 1/2 g because we want our acceleration is pulling us down. So let's think about this. If this is our equation, we take the derivative to get velocity. What's the derivative of a constant?
Nothing.
What's the derivative of something times t? And then minus gt. Right? And then if we take that derivative to find acceleration, we're left with
G.
negative g. So our acceleration is our force of gravity. Crazy.
Oh, wow, I get it now, negative point.
Okay. So, well, we're going to change this to John. Okay? Because it's a baseball problem.
Hey, it's Sean's birthday.
Is he sitting on the bench in the foul?
Suppose John went outside and was actually able to throw a baseball up at a velocity of 100 feet per second. How high would the ball go? Let's assume he's throwing. When he releases the ball, let's assume it's 5 feet off the ground.
So he's reached nothing. So is it like 3 feet?
Maybe he underhanded it. Okay. Anyway, what would our position equation be? -1/2. Which force of gravity are we going to use? 32. What's our initial velocity? So 100 t plus our initial position 5. How high will the ball go? How do we figure that out? Somebody please raise their hand if you have an idea of how we determine that. Jimmy. The maximum of what, first of all? Okay. Do you agree?
I agree.
Yeah. Rebecca?
Where you set the velocity equals 0 and solve for the critical points, and then use those time chart to find and then put it back into there.
Okay. Did Rebecca and Jimmy just describe the same thing?
Yeah.
They did, didn't they? Awesome. So we're all on the same page. Because we have people agreeing with Jimmy, we have people agreeing with Rebecca. They both describe the same thing. So we need the velocity equation, which is -32t plus 100. And we set that equal to 0.
Where did 32 from first?
Since we're in feet per second, we're going to use 32 as our gravity.
Okay.
If it was meters and seconds, we'd use 9.8. Okay? T equals what, Jimmy? Okay. Carly, what does 3.2 stand for?
Time.
The time that it hits our height, correct? But I'm asking for how high will the ball go? So Nathan, what do we do with 3.2?
What did you say?
Is it exactly 3.2?
No, 25 minutes.
It's 3.125? We need to keep it exact as we can. Okay? So we need to plug that into position.
Well, you're not wrong.
Does somebody have it for me?
168.75.
168.75?
I got 161.25.
Yeah,
That's what I
that.
got.
Wow.
Then why do you ask us for the answer?
Because I want you to actually participate in class. Okay, so feet through it, 161.25 feet. Nice job.
Are you plugging in for time?
Oh, it's like I've never done
So it's always going to follow the model, -1/2 g t squared. Oh, gravity.
Every day.
All right. Another example. And this example will take us to the end. Okay. A calculus book somehow finds itself on top of Papillion Vista South High School. For unknown reasons, it falls off the side of the building. How fast is the book falling after 2 seconds? So first of all, yeah.
There should be multiple books being thrown off.
Let's talk about our position equation. And we're going to go ahead and we're going to use, it doesn't say anything about,
Books cannot find.
it doesn't say anything about units, so I'm going to say let's use meters and seconds. So let's talk about our position equation. -1/2 times 9.8 times t squared. If something is just falling, does it have initial velocity? No. Do we know how high the building is? We don't really care. Okay. We can say that the top of the building is our height 0, and we can figure out everything else from there. Right. Right. So we're just going to keep it as this, okay? So how fast is the book falling after 2 seconds? That means we need to evaluate its velocity, derivative. Both describe the same thing. So our velocity is -9.8 t. So our velocity after 2 seconds would be, what? Okay. It's negative because it is falling. So we are falling at 19.6 meters per second. Okay. All right, how far has it fallen in only half of a second? What do we do there? Okay, our position. Probably can't do this in your head. Okay, it's negative. Carter mentioned it would be. That just means that it fell 1.225 meters. Okay. Now, how long would it take for the book to fall 50 meters? What are we doing there? Okay, so our position is this. If I want it to fall 50 meters, that is our position, and then we need to look for the time. Right? So we need to multiply, or we need to divide this over,
And then square root it.
and then square root it. So really, if it's falling, this would have to be a -50, right? So that we're not square rooting a negative number. Okay?